Hello. Okay. Thanks for that introduction, Brian. So my name is Kaushik Veeraraghavan. Today I'm going to talk to you about Frost, a new system that can efficiently detect data races and survive their harmful effects at runtime. So over the past few years, multi-core and multi-processor machines have become ubiquitous. Increasingly, application developers are writing their programs in a multi-threaded fashion so they can fully exploit the available hardware parallelism in these new machines. Unfortunately, as the previous few talks have shown, and many of our experiences have told us, it's really, really hard to write correct multi-threaded programs. This is because multi-threaded programs are susceptible to a wide range of concurrency bugs. These include data races, atomicity violations, deadlocks, and so on. In the rest of this talk, I'm going to focus on a specific type of concurrency bug called a data race. So a data race is comprised of two instructions, at least one of which is a write, that access the same shared variable without their accesses being ordered by any synchronization operation, such as a lock or a mutex. So this example is a real bug that occurs in MySQL. As you can see, the proc info variable is not being protected by any synchronization operation. Hence, if the threads or the instructions shown in blue and red interleave, as I've shown you here, where the instruction in red executes between the instructions in blue, this program is going to crash. Now, in practice, it turns out that data races, we as a community have to really care about these because they can have potentially unbounded effects. And it turns out that some of these effects can be catastrophic, too. This is evidenced by the Therac-25 radiation overdose incidents, which led to multiple deaths, and the 2003 Northeast U.S. power blackout, which affected about 45 million residents in the U.S. and about 10 million in Canada. Now, when we think about data races, there's two fundamental ways to address them. The first thing that you can do is you can say, OK, I'm going to run a data race detector, which is a tool that can be used to test out programs in development prior to shipping out the software. Now, we'd ideally like three properties in a data race detector. The first thing is we want it to have high coverage. So what we mean by this is, given a program, we want the tool to tell us all the harmful data races that exist in the program. The second thing that we want is we want the tool to be accurate. We don't really want it to give us a whole bunch of false positives, because that costs us time in going through these lists of bugs. And finally, we want it to run with low overhead so we can find the maximum number of bugs in our program in the limited amount of time that we have for testing. So as the table here shows, unfortunately, current state-of-the-art race detectors have to consider fundamental trade-offs if they have to operate at low overhead. For instance, Thread Sanitizer adds upwards of about 30x overhead for native programs written in C and C++. There are systems out there like FastTrack, which greatly reduce this overhead down to about 8.5x by restricting themselves to function on managed languages like Java. Orthogonally, another approach that we could take is, OK, we don't really detect races in the entire program, but we're going to sample. So this, systems like Data Collider and Pacer do this very effectively. The problem here is that they reduce coverage, but yes, they do function with very low overhead. In this talk, I'm going to show you a new system called Frost, which can achieve high coverage for native programs and detect data races by adding less than about 3x overhead. We can also use Frost in a sampling mode, where it adds, for sampling about 3.5% of axes, which means 3.5% coverage, it adds only about 18% overhead. Now, as I told you, testing time is always limited. Hence, there might be some bugs that slip past our testing and slip into the production code. So a second goal that we'd like is we want a tool that can detect unknown data race bugs that happen to manifest at runtime and survive the harmful effects so our program can continue executing on. So in the rest of this talk, I'm going to describe how we achieve our two goals with two new techniques. These techniques are outcome-based race detection and complementary schedules. We realized our ideas in the new system that we call Frost, which is a new and efficient way of detecting data races and surviving their harmful effects at runtime. I'm going to close off with an evaluation of our system. So we started off thinking, well, why is it that current data race detectors add so much overhead to the program? So we realized that current data race detectors work by analyzing the events executed by a program. For a multi-threaded program running on a multiprocessor, analyzing these events requires tracking the shared memory accesses performed by the different threads. Unfortunately, these accesses are so frequent that it adds very significant overhead to the program runtime. So in contrast, we are going to propose a new idea, which is we're going to run multiple replicas of a program and analyze the differences in state that are generated. So for instance, the bug here that I've shown you on the left is the MySQL example that I started off with. Let's imagine that we can have a second execution of the program, as I've shown on the right. Now, we can just look at the output of these two programs and detect that a data race has occurred. So our goal then is that we want to run these multiple replicas, and we want it such that these replicas diverge if and only if a harmful data race actually occurs. So this is a difficult goal, and we're going to go about achieving this by breaking it into two steps. The first thing that we want is we want to aim for no false positives. So specifically, we want to know that if our replicas happen to diverge, it is because they have encountered a harmful data race. Now, if we're running these independent replicas, the first thing that we need to ensure is that they execute non-deterministic events the exact same way. So what we do here is we ensure that all replicas of the program observe the same program input and that they obey the same happens before ordering of synchronization operations and system calls. Given these two properties, we now know that if the replicas do diverge, it's because they've encountered a harmful data race. We really want this first property, but we want to go beyond this. We want the additional second property that a harmful data race does cause replicas to diverge. We achieve this through a new idea that we call complementary schedules. So the idea in complementary schedules is that we want to try and make these replicas, they're already observing the same inputs and non-deterministic events. We now want to go further and try and make them as dissimilar as possible. So specifically, if we have two instructions, A and B, that are unordered, what we'd like is we'd like one replica to execute the instruction A before B, and the second replica to execute the instruction B before A. So you might look at this and think, well, this is a little bit abstract. So I'll try and make this clear with a concrete example. Oops. All right. So here's a simple program. There's just two instructions that raise. One of them sets a pointer to null, and the second one dereferences this pointer. In the execution on the left, the setting to null occurs first, which is the instruction in blue. We see that the program crashes. In the execution on the right, we see that the unlock occurs first, and then the pointer is set to null. This execution succeeds. The key point here is that there are these two instructions, and based on their simple ordering, the program can have drastically different outcomes. In this case, it's very obvious that they have a different outcome because of the crash. But it could very well be the case that the difference is much more subtle. For instance, there's some slight divergence in memory state or in the register values. So we do not know a priori that a data race exists in this program. So what we'd like is we'd like to run these replicas which schedule unordered instructions in opposite orders. By our definition, since one of these orderings leads to a harmful outcome, one of the replicas is going to break while the second one succeeds. If our goal is data race detection, we can notice this divergence and immediately flag a race. If our goal is survival, one of the replicas executes the correct ordering and hence survives the data rate bug. All we have to do is identify this and continue on. So you might be thinking, well, this is great for the simple example, but how are we going to do this for an arbitrary program, right? There's lots and lots of instructions. So, and we don't actually know what the racing ones are. So our insight here is that we can try and flip all pairs of unordered instructions in a program. So how do we go about getting this, right? What we need is, to start off, we need a total ordering of all the instructions in the program. One way to achieve this is to constrain our multi-thread program so only one thread of the program runs on a processor at any given time. Now, this thread of the program is allowed to run non-preemptively until it naturally blocks either on a system call or on a synchronization operation. At this point, we would context in a second thread, and so on. And what we would do is we would log the ordering with which these threads are context switched on the processor, like, say, T1, T2, and T3. Once we get this total ordering, we can then run a second replica which reverses the ordering of the threads, as in it runs threads in the order T3, T2, and T1. Now, effectively, what we're doing here by only letting one thread of the program run at any given instance is that we're constraining our program such that we're taking this multi-thread program and time slicing it on a uniprocessor. Now, the nice thing about this algorithm, really, is that it allows us to provide certain hard guarantees for intervals of execution in which a data race can lead at most to a single harmful data race bug, and there's no synchronization operations to contend with. So let me show you what these guarantees are. So previously, I showed you a simple data race bug. Now, we say that the ordering of two instructions that leads to an error is a failure requirement. So in this example, there's a single failure requirement, as in if the instruction in blue runs first, the program will crash. Now, if it turns out that for a given program, there's more than one race involved that leads to a harmful data race bug, we say that the bug is of type 1 as long as all of these failure requirements point in the same direction. So let's say going from left to right. Now, since replicas running these complementary schedules execute such that each thread is executed in a given order, we know that given our two replicas, one of them will always schedule the instruction in blue before the one in red, and hence will crash or fail, while the second replica will always execute the instruction in red first, since they're running with reverse orderings, and hence will survive the effects of this bug. So we can guarantee data race detection for synchronization-free regions, as we will notice this divergence. Further, in the case of subtle error, if we can identify which replica is correct, we can use that surviving replica to continue program execution past the bug. A type 2 data race bug is slightly more complex because it's got multiple failure requirements that point in opposite directions. So for instance, in this MySQL bug, there's two failure requirements. Both of them have to occur for the data race bug to manifest. In other words, the instruction in red has to interleave between the instructions in blue for the program to crash. Because complementary schedules execute threads non-preemptively, neither of our replicas is going to have the instruction in red interleave between the instructions in blue. Hence, both replicas are going to survive the harmful effects of this data race bug for synchronization-free regions with a single harmful bug. Now, so far, there's two limitations to this work. The first thing is, if you observe, all of my replicas are constrained to a single processor. And the second limitation is, well, a real program does use synchronization, and it's going to have multiple bugs. What I'm going to show you next is how we improve our performance, and then I'll describe how it turns out in practice that despite the fact that the guarantees I've shown you so far can only be provided for sure for synchronization-free regions, they actually tend to work really well in practice for real bugs. So as I showed you here, our algorithm constrains these threads to run on a single replica. This is great because we can record the ordering of the threads. So let's say we have one replica running on CPU 2 with T1 and T2. We can have a second replica running on CPU 3 with the reverse schedule. So we can efficiently control thread schedules, but we're wasting all of these other spare processors on the machine. To improve performance, we're going to leverage uniparallelism, which is a technique that we introduced in our prior double play work. The insight in uniparallelism and in double play is that we can run a second multiprocessor execution of the program. This second execution allows each thread to run freely on its own processor. As this multiprocessor execution is much faster, we let it run ahead and use it to speculatively generate checkpoints, which can be used to start the next interval of the uniprocessor executions in parallel. Observe that this is just like a processor pipeline, and really it can scale easily as we increase the number of cores. Now, we realized this design in Frost, which is a new system which is built upon the double play infrastructure. Frost runs 3 replicas for each interval of execution. The leading replica on the left provides us with not just the checkpoint, but also a log of all the non-deterministic events, which is all the partial ordering of system calls and synchronization operations. The 2 replicas on the right replay this log and run with complementary schedules. So you might say, oh, well, you're taking a single interval of execution and you're running it 3 times. Doesn't this impose a 3x overhead? So you're right, there is a 3x overhead. But the cool thing here is that there is only a 3x overhead. So unlike previous data race detectors, which used to function at 30x or more, our cost is 3x. So how does Frost actually go about detecting and surviving these races? Well, as replicas execute, Frost must infer whether any of the replicas have failed or experienced a harmful data race. Frost accomplishes this by first checking if any of the replicas exhibit a self-evident failure, like a crash or an assert, or something along those lines. If so, it can easily identify that a particular replica has failed, and then select a surviving replica to continue execution on. It could also very well be the case that a harmful bug leads not to an evident failure, but to something that requires understanding program semantics, like mismatched output or corrupted output. In this case, Frost also explicitly compares the replicas to check for divergences, which is it checks that the order and the value of all system calls and synchronization operations executed by the replicas are identical. And it also checks that the register and the memory state of the replicas at the end of each epoch is identical. If it turns out that they've diverged, well, there's a data race. Now, one cool thing that Frost inherits by building atop the double play system is that we can guaranteed reproduce any execution in which there's a data race. So what this allows the developer to do is, given a particular recording, he can run that offline as many times as he wishes with all of his custom tools, which understand what was it about this particular execution that caused the bug to manifest, what was the interleavings, what was the program input, etc. Additionally, Frost can also analyze the outcome of epochs to survive the harmful effects of a data race bug. This explanation is a little bit more involved. Please bear with me. Overall, our strategy in Frost is we want to use Occam's razor. We want to derive the simplest possible explanation for a given set of outcomes. So basically, we want to try and say, how can I explain the set of outcomes with the minimal number of data race bugs? And given a matching number of data race bugs, we want to try and condense it down to an explanation that involves the fewest number of failure requirements. So in the outcomes that I've shown you here, the first alphabet refers to that of the leading replica, while the latter two highlighted ones belong to the trailing replicas running complementary schedules. So what I'm going to do is just roll back to the previous checkpoint and retry executing that interval with the hope that the bug is non-deterministic and I can continue past it. The simplest explanation for these set of highlighted outcomes is that there's a single bug of type 1. This is because there's two different outcomes for the three replicas, or the trailing replicas differ. In this case, Frost sees if either of them has experienced a self-evident failure, which we denote by F. If one of the replicas has failed, it chooses the other one to continue execution on. But if they mismatch, we just roll back to the previous checkpoint because it's not clear which replica is valid and run additional replicas to see if we can decide that. The next simplest explanation is a single type 2 data race bug because we observe that neither of the trailing replicas which run complementary schedules fail. In this case, we can just commit either of the replicas and continue on. And last, we have these confusing outcomes, which really indicate the existence of multiple data race bugs. So Frost's strategy here is to roll back and drastically reduce the size of the epoch or the interval and try and separate out these data race bugs so it can encounter them one at a time and analyze them individually. So this leads me to my next part, which is, as I mentioned before, our guarantees have some limitations. I'm going to briefly describe what these are. There's more details in the paper if you're interested. So broadly, if it turns out that one of these intervals of execution happens to have multiple bugs of type 1, then Frost might sometimes, Frost would detect them, but it might not be able to survive them. So in this case, our strategy is to roll back to the previous checkpoint and drastically reduce these epoch length to try and separate out the bugs so they're encountered one at a time. Now, it could also be the case that there are intervals in which more than 2 threads are involved in a particular harmful data race. Now, if it turns out, as it turns out, because we run 2 replicas with complementary schedules, 2 replicas are insufficient to flip all of these racing pairs. So in this case, we have a problem that's akin to priority inversion. In the paper, we've described a heuristic that we use to deal with the situation, and it turns out to actually work quite well in practice. A third limitation is that when we introduce these epoch boundaries, they actually function as false barriers which didn't exist in the original program, and this might also cause Frost to miss certain types of certain data races. So in order to mitigate against this limitation, we take care to insert epoch boundaries only very infrequently. And additionally, we ensure that all the threads are executing system calls in the kernel when an epoch boundary is drawn, so as to not force a data race. Lastly, as I showed you, for type 2 data race bugs, it could very well be the case that both of the complementary replicas arrive at the end of an epoch with the same matching register and program state. In this case, theoretically, we can't guarantee detection, but it turns out that in practice, for most harmful data race bugs that we've encountered, there's some slight difference in either the program state or in the register state or output that allows us to recognize or detect the type 2 bugs. Now, in order to ensure that these limitations didn't really hurt us much, Our first evaluation of Frost was on a concurrency bug suite. This is a well-known concurrency bug suite used by people in the OS and the architecture community. We evaluated Frost against all of the data race bugs in this suite. There were about 10 of them. And as we tested Frost against these, we also discovered a previously unknown and potentially malign data race bug in glibc that we reported back to the community. As the highlighted columns indicate, these 11 data race bugs manifest in all sorts of different ways. Some of them crash, some of them lead to double freeze, assertions, etc. And there's also bugs which show up as weird semantic, which trigger weird semantic differences, such as corrupted or missing output. The key takeaway here is that in every single case, Frost correctly detected and survived all 11 of these harmful data race bugs in each of the 5 trials that they were encountered. This is really good for us because it turns out that, yes, we do have these theoretical limitations, but in practice, they don't occur as much or as frequently. As the last column indicates, we found that recovery is very fast. Generally, it only takes fractions of a second to recover after detecting a race. And this is really good because programs have harmful races are very rare in real programs. Now, additionally, we wanted to compare Frost coverage to that of a traditional dynamic happens before data race detector. To ensure an apples-to-apples comparison, we ran an execution with Frost, and then we ran a traditional dynamic happens before vector clock-based data race detector on the replay. As the highlighted columns indicate, the key takeaway here is that a Frost coverage is equivalent to that of a traditional happens before dynamic data race detector, and so Frost can be actively used during program development. In every single case that the traditional detector identified a harmful data race, Frost also identified the same harmful data race. Now, there's a few bugs here, like Apache 2 and 287, which have zeros. And really, what happened here is, in our limited testing time, this bug never really occurred because we weren't really trying to ensure or manipulate the benchmark to actually have these races show up more often than they really do. Additionally, as the last 2 columns indicate, Frost greatly benefits from its technique of filtering out data races that do not lead to divergences in the outcomes. And when Frost decodes a data race, the developer just has to spend the effort in fixing those races because instead of having to comb through thousands and thousands of bug reports, as with the traditional data race detector, to identify the few harmful ones that actually exist in the program. We also evaluated the throughput overhead introduced by Frost. And it turns out that for applications whose CPU demands are so low that there are spare cores available on the machine, Frost doesn't really add much overhead. So given an 8-core machine, when we run these applications such that they consume slightly more than 2 cores, we find that Frost only adds 3 to 12% overhead. Now, for server applications like Apache and MySQL, we also find that these applications turn to be bottlenecked on network and disk I/O respectively, and hence they're unaffected as we vary the number of cores from 2 to 8. However, if there are applications like PBZip2 and pfScan, which are embarrassingly parallel and can scale to take advantage of all available cores, then we find that Frost can add up to 2x overhead. Now, this is the case with any active replication system. If there's no spare hardware to amortize cost or to hide the cost, then, well, there might be an increase in overhead. To summarize, in this talk, I've introduced 2 new ideas: outcome-based data race detection and complementary schedules. We find that we realize these ideas in a new system that we call Frost. Frost is able to efficiently detect data races with high coverage. We find that given spare cores, it adds only about 3 to 12% overhead, and in the absence of spare cores, the overhead is about 3x. We've also found that Frost survives all harmful data race bugs for the benchmarks that we've tested against. Thanks. I can now take the questions.
George?
Go ahead, George.
George Candea, EPFL. So this is actually a follow-up on the 2 questions asked after the previous talk, and I think both talks use some terms rather loosely. So the previous 2 questions were, what's a race, and then what's a harmful race? You were a little bit more specific, but I think both of your definitions are wrong. So A harmful race, you say, is one in which you have, sorry?
Can we turn that into a question?
Yeah.
Yes.
He's still finishing the question.
So when you look at a harmful race, you say that state divergence is what makes it harmful. The question is that really true?
So what I'm saying is a harmful data race is harmful because it leads to one of two different things. The effects of a harmful race are what we really care about. Okay, so that could be a particular data race which in a execution, if it does not change, if you have multiple executions which reorder racing instructions, and it turns out that those instructions, when reordered, do not change either lead to an immediate crash, which is change immediate output, or lead to divergences in the memory state of the program or in the register values, then for that particular execution, that race is not harmful. So you're right, the harmful data race exists, but one property of dynamic data race detectors is that they can only analyze and pinpoint races when a harmful effect is encountered. So in our case...
No, so I'm referring to the other side. So you do have a divergence, you do have a difference in state. The question is, but actually it's more of a statement, the conclusion that that's a harmful race is incorrect.
Perfect. Yes, you're very right. I totally agree with you. And if you actually look at this example here, you'll see that Frost, for several of these cases, has the number 2 showing up. What that means is it's identified one harmful race and one benign race, which happened to lead to an output divergence. And I can give you a very simple example where this happens all the time. That's a master thread, and there's 2 worker threads. Okay? The master doesn't care which worker actually compresses data. It just wants one of the workers to compress data and write the output to a file. The master doesn't care if the outputs are ordered, worker A does first, and then worker B does first, or B does first and A does first. Frost will identify this as a harmful race. Why? Because it'll say that depending on the ordering of whether A finished first or B finished first, we can have different outputs. But in reality, it's a benign race. So yes, we're doing our best to minimize these false warnings that we generate. And as you can see, compared to a traditional detector, like a generic happens before data race detector, we do drastically well. We can reduce, from MySQL 644, we go down from 2008-99 to about 2. One of them is harmful, and one of them isn't. So there's categories of these benign races which might have outcome divergences that we identify.
Okay, so my plea would be to not call them harmful if they're not harmful.
They're not harmful.
Sure. So they're potentially harmful.
Perfect. Thank you. I'll start using. I'll add that clause in the future.